Hello. So today we're going to be doing a different but very similar coding pattern. It's called merge k. So basically, you want to merge k different lists, or like k different. It doesn't have to be lists, but I think they're typically lists though. But like merge k things into one bigger one, and in this case, we're doing merge k sorted lists. Um, this was actually one of the first, if not the first, hard problem that I did. Um, but I did that back a long time ago. Um, so I don't know. With that being said, we can just get right into this. You're given an array of k linked lists. Each linked list is sorted in ascending order. Merge all the linked lists into one sorted linked list and return it. So basically, if you look at this example, 145, 134, 26, you merge into a 1, 1, 2, 3, 4, 4, 5, 6 type of list. If it's empty, then kind of just do whatever. So with that being said, we can just get into the problem. Uh, we're we're going to be using a heap queue for this because we want to sort things in increasing order, right? And what better thing to help us than a heap queue or like a min heap, right? So here we're going to define a heap, which is just empty. It's an empty list, but that's how it works in Python. We're going to create a for loop for I in range of the length of lists. um, we're going to be doing stuff, right? So basically, if list I, so basically if it's an actual like item, right? Um, then we'll actually care about it. If not, we don't care. Um, so, for example, like if like in this case, right, there are no lists in lists, so we don't care. And there's one list, or like this is how it represents a linked list, right? There's one linked list, but there's nothing in there, so it's still null, so we don't care, right? So this is checking to make sure that there is a node that we do care about. Then we'll push it onto the heap. And then here is like, I guess where it's a little bit, trickier. Um, Here we're going to be putting in the value and the index at which it is in the lists array. The reason why we have to do this is because since we're not defining the class list node ourselves here, and it doesn't allow us to, we can't just override the less than function, right? And then just do like return self.value is less than other.value. Like we're not able to do that, right? Because we don't get to define list node ourselves. So we have to, make it work in like the min heap as is, right? So here we'll put the value of the first node in the linked list in this index, and we'll put in the index as well. So basically, it'll sort by the lowest value first. But if there's a tiebreaker, it doesn't really matter. Like in this case, right? If we use this one or this one first, it doesn't really matter. No one really cares about like which of these ones actually goes first, as long as the ones do show up first, right? So this will give us a heap with at least valid list nodes that we care about, and they will be sorted from in increasing order, in ascending order, right? So now we come down here, we're going to have head list node. We're just going to create a list node with a value of -1. This list node is just a holder so that we can pass on, so we can attach the following linked list, or like the linked list nodes, and then we can just return the answer from there, right? And we're going to have a mover, which is just something that will move along the linked list because in a linked list, you can't just access an index in the linked list, right? You have to, move along with it. It's all with like pointers. So we'll have a mover, and so that we don't lose our position with this holder list node object right here. So while heap, which just means, while there's stuff in the heap, we want to do stuff, right? We're going to do an underscore index is equal to heap pop from the heap. The reason why we use this underscore is because we don't actually care about the value. We really just need the index, right? So we're going to come here. We're going to do mover.next is equal to list index, oh not I, index, right? Because this will attach the whole list node to the end of our current. So at the very beginning, it will just be the it'll attach a whole list node of whatever index we get to the back of this. But then we'll eventually break it up, and then we'll start manipulating it all, right? So this will just set the next to whatever linked list is there, and then mover equals mover.next, because we only want to keep the next list node, right? We don't know if moving further on will, like, if we keep the rest of the list, if it's actually the right order. For all we know, it could be the right order, right? But we can't guarantee that, at least with the logic here. So we will just move it one over, and then now we'll make a check to see if we want to put this list, the rest of this linked list back into the min heap, right? So this will check if the .next of our current list node is actually valid. If it isn't, then we won't even bother. Like, we can't push it onto the min heap, right? So we won't even try. So now we know that there is something there, so we'll just move it one over. So it's .next, right? So we just move the pointer over by one, and then we'll push it onto the heap with a list index .value and index. So basically, we'll push the next value because we moved the pointer over, right? We'll push the next value as well as the index back onto the heap, and then this will ensure that it is in sorted order. And then so after we finish, so then if we don't push anything for a while, this will eventually exit, right? Now we'll just return head.next, because we don't actually want to return head, because head is just a holder list node, right? So we want to push the next part, or we want to return the .next, because that will give us the right value. Yeah. So that's the problem. We'll submit it, and yeah, it runs. That's what we want to do. So yeah, thanks for watching. Goodbye.